So it's truly a pleasure to have Giorgio give the seminar today. This was arranged quite a long time ago, even before Giorgio got the prize. And congratulations again to Giorgio. Please mute yourself. But if you want to ask any question, please unmute yourself. Okay, Giorgio, it's all yours. Go ahead.
Thank you so much. Now, I will try to speak about spin glass theory and some multiple equilibria. The idea is to discuss this concept in general and also to see what is the situation of the theory from a rigorous viewpoint. Now, the idea of multiple equilibrium is something that started in the 70s in biology, and that was in the theory of evolutionary theory of punctuated equilibria. Now, the idea was very simple. I mean, the evolution of the species is not a continuous gradual process, but a long period of stasis where it's practically no change in morphology, and this period of stasis are punctuated by rare bursts of evolutionary change. More or less, one could say in modern language, very far from the language of Eldredge and Gould, that living species is stay in some kind of a landscape and they stay in the minima. They can go from one minima to another minima to a tunnel, and this will be a very fast event. Now, for example, another case where the idea of multiple equilibria is crucial is the modern theory of memory that started with Hebb after Litre, Hopfield, Daniel Amit, and the idea that part of the brain that is responsible for memory may stay in a very large number of equilibrium states, and each corresponds to a different recalling of a different item. And the fact that there are such a large number of states is a reflection of the fact that we can memorize so many items. Of course, these are not real equilibrium states, a metastable state, but for biological things is fine. Now, some ideas of multiple equilibria have been done in Kaufman's paper in 1948, in which we wanted to study glasses. And this has been discussed later on by many other people. For example, a remarkable paper of 1969 of Colson wrote as the idea that essentially is explained this idea very carefully, that a low temperature or a supercool liquid explore the phase space and makes activated jump between different amorphous minima, which are separated by potential energy barrier, and the fact that there is a tunnel between one minimum and another minimum explains the huge increase of viscosity in glasses. The number of phase space regions was supposed to be exponentially larger in this case. Now, let's go to modern, let's say, to the theory of spin glass. And I think that the modern theory of spin glass starts with Edward Anderson model, which is really the simplest model that we can think for three-dimensional spin glasses. And the Hamiltonian for this model was essentially a nearest coupling interaction between spin and the crucial point. Of course, we could have a magnetic field here, and you may have this, and you have the coupling J, a random coupling, and they are different to zero only if the points are near neighbor one with the other one. They are independent random variable, and of course, you can write this Hamiltonian with Ising spin, Heisenberg spin, and so on. But for the simplicity, let's stick to the Ising case. Just one crucial point of this paper was not only the introduction of the replica method and so on, but was also the observation that low temperature spin glass sample will have some kind of magnetization. However, each sample, because it's characterized by different J, will have a different value of the magnetization. So the great idea was to introduce all the parameters Q Edward Anderson, which is the average over the system of the manipulation square. It will be zero at high temperature in zero magnetic field and different from zero in zero energy phase. So we have another parameter, although we do not know in which direction the manipulation point, we have another parameter that we can discuss. Now, the real novelty, I mean, the one point that was very important for future development was the use of the replica method. Let me recall briefly what the replica method is. Essentially, what we want to do for each sample, we want to compute the partition function. For each sample, we want to compute the partition function here, take the log, and after getting the free energy. And now the partition function for each of the samples is defined in the usual way. Now, just because we have an exponential inside the log, it's difficult to make the computation. Now, the average of J can be done using what Anderson himself called an autonomous trick. You will do the two steps. You write this quantity to the power n as the product of n factor z to the j. In this case, we can do the average of j, and we can get formula that involve the integral over some kind of Q variable, and which is an integer number variable. Now, you can take the variable n not to be an integer in this formula. Of course, in this formula here, n, just because you are doing n equal to 0 limit in non-integer. And however, you try to use the two formulas, the one that is valid for integer number and the one that is not valid for non-integer number. Now, one can ask who invented the replica method. Well, I think that all the reference to replica goes to Nicola Doresme, who discovered the square root of x can be written x to the power 1/2. And in modern times, Robert Brout used replicas in a paper of 59 for random ferromagnetic system. And as far as I understand this paper, he used the replica method for simplifying the diagrammatics without discussing too much deeper about replicas. And essentially, he does not use closed formula. Essentially, he organized the cumulants in power n and consider only the term m to the power 0 from the random system. So it takes n replicas, and the quench case is n equal to 0. Now, of course, replicas were used by the GEN for self-avoiding polymer. Essentially, his idea was that you have the all-Wilson result for the n symmetric theory, and he noticed that he can extend this result to n equal to 0 because n equal to 0 was described in self-avoiding polymer and computing the critical exponent. Now, the idea of developing an n symmetric theory, theory 5 to the cube, is in terms of closed trajectory, is contained in old paper by Simancic, 69, but the idea of using for real self-avoiding work is clearly by the GEN. Now, the same theory can be formulated also for as a Laplace plus random imaginary plus random potential. And the replica group in this case, as I stress here, is ON, and something similar can be done for localization. Now, things becomes more sharp with the introduction of the Cherrington-Kirkpatrick model. The Cherrington-Kirkpatrick model is similar to the SK model. The only difference is that all spins are connected one to the other one, and the interaction square is 1 over n. And also in this case, the J are independent random variable. Now, the Sherrington-Kirkpatrick model has immense influence on the field. First of all, because as usually, as I think it was stressed by Lebowitz years before, when you have in infinite range model, the solution of the infinite range model is what people can call the solution of the mean field theory. So the mean field theory and the solution of Sherrington-Kirkpatrick model are more or less a synonymous one. And also what is crucial in this model, that we can start in great details just because we are supposed to solve it exactly, we can see if things are okay or not, are good or not. Now, Sherrington-Kirkpatrick proved that for a system n spin, it's possible to write the exact replica formula. So this was important, the formula was exact. Is the average value of the partition function to the power n can be written as an integral over symmetric n by cross n matrices with 0 on the diagonal. So this part of the formula is exact. And now what they were doing, what people usually do in this case, is to do a center point expansion and taking these things as the value of Q star. And where Q is in some sense a maximum, the minimum of the function f. And now they also did the next innocent looking assumption that this minimum was for matrices that are symmetric, as possible symmetric, that all non-zero elements out of the diagonal are equal to common value Q. However, as noticed immediately by Sherrington and Kirkpatrick, the results were not consistent and the entropy was negative at low temperature. The result, the reason of this negative result was mysterious until Dermeda and Towles proved that these things is not a minimum. But we may ask which is the value of the minimum. But before asking which is the value of the minimum, we have to realize that in this context, the word minimum is a little ambiguous. For example, the natural definition, there are two natural definitions of minimum or local minimum, let's say, that we can, given a function, we can compute the Hessian matrix. And if the Hessian matrix has non-negative eigenvalue, it is a minimum. It may be a minimum, may be a set point. Of course, if the Hessian has negative eigenvalue, self is not a minimum. Now, if we take just the trace of Q square and we would expect the trace of Q square is as a minimum a Q square equal to 0, we see that as function n, it changes sign apart from the prefactor 1 of n when n is equal to -1. So this quantity as function of Q square of Q as a maximum at Q equal to 0. However, it can be argued that the good definition of minimum is this one of non-negative Hessian. Okay. Now, there have been some attempts, Blandin, other, and so on, to use in SQ star a matrix where all Moore and so on, where matrix elements were not equal to Q. For example, the case, I think, of Blandin and others was that where we have n replicas that are divided in some groups with n over m replicas, we are m integer, and the value of the matrix depends on which group the index belongs to. Now, if you do this type of computation, you find that trace of Q square is m equal Q square, m equals multiply Q0, and is Q1 square. Now, there is something that may be strange in this formula, that you see that if you take, for example, m equal to 2, which was a solution of Blandin, you get that m thinks this has a positive sign here and a negative sign here. And in 79, I had the intuition that one should take also m non-integer. Now, if you take m non-integer and you take m between 0 and 1, you see that now these things becomes a reasonable quadratic form. And the idea was that one should maximize the free energy both at Q0, both at Q1, and both as function of this mysterious parameter m, which was a continuous, which is now is continuum variable. And now what it turned out that the first step, what people call one replica symmetry step, breaking at one step, the results were much better, and the entropy was negative, but only in a very strict temperature range. After repeating infinite times this procedure, the final formula were fully consistent in the sense that entropy is always non-negative. Now, if you look to the group theory, now you see that usually when you break, you have a group theory that invariant under symmetry group as n. When you break spontaneously the theory becomes invariant under a smaller group. Now, indeed, what happens? Suppose that n over m that you have this. Sorry, you have some identity of this type, and this when n is sorry, this should be n over m. I'm sorry. And when n and for m is integer, so okay, forget this formula. Anyhow, what the idea essentially that at the end, when you go send n equal to 0, you get that the symmetry group of 0 element behaves as a subgroup of S0, so this becomes an infinite group. Of course, it's clear that this kind of idea do not make sense from the mathematical viewpoint. However, if you look to the final formula for the free energy are completely reasonable in the sense that you get a well-defined expression. Of course, one has to define that this functional is well-defined, that the maximum well-defined, and so on and so on. And I think that is quite surprising that after you finish a computation, that the order parameter is a function. Now you said the order parameter is a number. Here, the order parameter is a function, and there is a function which is defined from x goes from 0 to 1, and it was absolutely unclear from this type of expression, and also for this kind of equation here, which was the meaning of x, which was the meaning of qx, and so on. However, the thing that was quite impressive, that when you do this type of computation, you get with the accuracy of computer simulation. I mean, I'm very grateful to Sherrington and Kirkpatrick, or to Kirkpatrick and Sherrington. They've done very careful computer simulation for the energy, because it was crucial for me in doing this type of computation to know that the original, which was the value of the energy at 0 temperature. So when I got the energy correct, I was very happy. And after I have no idea how to go on, after I started to work again on the problem, and finally, I discovered something that also other people were looking for, the fact that there are many equilibrium states, and that the formula that I were written in 79 can be written in terms of assuming that each sample has many equilibrium states. This state are labeled by an index alpha, and each state appear with at equilibrium with a certain probability W alpha. And now what happens is that each state is characterized by a matrix Q alpha gamma of the scalar product of the overlap of different between different states, and of course by this weight W alpha and this weight W alpha sum to 1. Now, essentially at the end we get that each sample has its own matrix Q, its own weight W, and the probability for each sample we can define a probability of having overlap Q, which is just given, sorry, this missing a delta function. Anyhow, the things that is happens at the end, the integral that we can have X of Q with the probability to have something average, some overlaps less than Q, is the inverse function of the Qx that was introducing without replicas. And now the interpretation Qx was clear. X is a probability, and this explains why X the range from 0 to 1. Now, in '83, I started to work with Mezzar, Sulla, Stulusa, and Virasoro, and we found something that was quite astonishing. The first things we discovered that the set of distance was ultrametric. Ultrametric, sorry, this is any beta. I'm sorry, I made a few mistakes here. This should be a beta, not a gamma. I will send you the correct version of the slides. I'm sorry. And now the idea essentially that ultrametric space is in a space where you cannot, if you go to in one step to a distance d, you do a second step of distance d, you always remain at a distance d. Therefore, in other words, you can say that if two circles of the same size touch, they are identical in the same circle. And also, one was able to prove that there were unexpected properties of this distribution, and for example, this identity over here for the average of over the spin of the square of two probability, the average over the sample. Remember here that this bar means average of the sample of 2 P of J. Now everything was full algebraic, but it was not very clear which was the physical meaning. Now, Mezzar, myself, and Virasoro in '85, they found a very simple way to characterize the probability distribution of the tree and the probability of the branching that depend on the function Q. I mean, what I have to stress is that just because the states, say, in ultrametric have satisfied their distance satisfy an ultrametric inequality, what we can put the state on a tree in such a way that the state are the branches of the tree. Each branch of the tree has a given weight W, and the distance between the state is proportional to the distance you have to travel to go on the tree from one state to another state. Now, what was done by Mezzar and Virasoro, my contribution was not very high, but I helped, that the probability of the branches that one can write in a very explicit formula for the probability distribution of this tree. And now, therefore, in this approach, therefore, what you can say, instead of starting from replica, you can assume that the probability distribution is the one that was computed in the replica method with Mezzar and Virasoro, with Mark and Miguel. And what is quite important in this situation, that we have an explicit formula not only for the tree, but also for the weight of the leaves of the tree. So therefore we can have this starting point. And if we use this starting point, we can ask that the probability distribution in average is the same for n spin plus 1 system as spin with n spin. which is essentially the cavity approximation. And if we do this way, we recover the replica equation for Qx. And we could also compute the free energy it coincides with the replica 1. Look, I think that I should mention here something that I think you all know, that last August or July, Miguel passed away. I'm very sorry about that. And however, it's a great miss for all of us. Okay. One point that also the infinite tree that we did in infinite weighted tree, I say weighted because all leaves have a different weight, is a well-defined object from a mathematical viewpoint. It was not clear from our paper. And well, in 1987, wrote a long paper that construct on probabilistic cascade to define the tree in a rigorous mathematical way. Is a construction of the tree starting from the roots of the tree and not from the leaves. And Boltzmann and Chisholm introduced the coalescent and reproduced a tree in other ways, starting from the leaves and going back towards the root. So this object is a very well-defined object. So we could say that the crazy form of the matrix Q is equivalent to this extreme probability distribution. So you can throw away the replica method. You have the probabilistic formulation. Everything can be computed in the probabilistic formulation. Sometimes it's simple, sometimes more complex. But now, once that if you have this probabilistic formulation, you have to assume the answers, both that the matrix that there is a tree, that the overlaps are ultrametric, and also the explicit distribution from the weights. Now, I was quite puzzled because at this stage, the fact that the matrix of the overlap is ultrametric is something that may look not so natural. While it was natural to do this choice in the replica method, from the probabilistic viewpoint, it was not so natural. And also, there's no reason that the probability of D is a descriptor which is composed by the Q and J, could be much more integrated. It was possible the automatic form, maybe only the simple form to be written, and the true solution was could be much more complex. And of course, the fact that the energy, ground state energy, agree with the simulations that became more and more accurate, was not a compelling result, because maybe the next step would only give one part of a 1,000 difference for the internal energy, but therefore it was not clear to me if everything was correct. And if the theory that I written, although started with, although extremely complex, was only the simplest form, and the real theory was much more complex. Now, the idea was, I mean, just plain with words, that we could write a free energy that depend on the probability description of the descriptors, and this free energy could be and the correct value of the free energy could be computed via cavity method, maximizing this way. Of course, this was a wishful thing because we did not have a way to write these things, and also why the free energy should be maximized. In this context, is not so clear. I mean, the rule to maximize is what comes from the replica method, but why should we maximize the free energy with respect to something? And also the things was extremely complex because the space of the scriptum is infinite dimensional, and the probability distribution of an infinite dimensional space is something extremely large. And I think that around 90s, in the beginning of the 90s, I was very skeptical about the possibility of finding proof that this probabilistic assumption, and therefore all the work who is done with probability was correct. I mean, the answer, the starting point was correct. And of course, to prove things with replica seems more and more difficult. However, fortunately, at this moment, the situation changed rapidly and mathematicians came to the rescue. Well, the first crucial step was done by Guerra. Guerra introduced, with Toninelli and others, introduced an interpolation that were able to prove that the true free energy was greater than the free energy computed with a replica method with any value Q. The proof is quite complex, long, but the advantage of this proof is that it uses only elementary techniques as integration by part and Gaussian integration. The great idea of Guerra was to introduce a function fz of f of z, where z is between 0 and 1, such that we know a priori that f0 is equal to f of q, f1 is equal to the true value of the free energy, and the derivative of f with respect to z is expectation value of something which is square, which is a positive definite. That was a completely change in the perspective, because first of all, it gives from an explanation why one should maximize, because the inequality in this case of the reverse of the standard inequality, and the free energy is greater than the free energy computed with the replica method, and therefore this gives us some hint that the things were in the right direction. And just a few months after Guerra result, Talleyrand twisted the result of Guerra, introducing, doing the same kind of interpolation with two replicas, and Talleyrand was able finally to prove that the correct the value of the free energy was just max of f of q. So the free energy, the maximum of the free energy is the max of f of q. And this was proved by Talleyrand. So the standard result, I mean, that the free energy is obtained correctly, maximizing the free energy, is something that was proved by Talleyrand. And now, however, the Talleyrand proof is something that goes on with inequalities, and however, it does not tell us which is the probability distribution of the descriptors. If the probability distribution that I was writing before, that the state organized on the tree and so on, is the correct one. Now, a very important paper was by Eisenman, Sims, and Starr, just after Guerra paper, that proved that generalized Guerra paper, and proved that if we consider the probability of descriptors that satisfy some kind of self-consistency cavity equation, you have that the free energy is equal to the max f of p. Now, this is the same formula of Guerra with Guerra as inequality. Of course, if you now write use the p that come from replicas, of course, this you get the right result, but this does not tell you that you may have other probability distribution P of D different from the replica, from the one coming from replica, that give the same result. So so the problem is this is the same equation that I was writing before, but on heuristic ground, now becomes a rigorous result. However, the probability distribution over the space of the descriptor is extremely large. Now, there is another idea by Guerra that was fundamental, And the idea was the following: instead of considering just the Sherrington-Kilpatrick model, you can generalize it by adding an arbitrarily small perturbation. And now what Guirlanda-Guerra proved that in this case, almost everywhere, there were an infinite number of identities that the probability P of D has to satisfy. This is stochastic. This is something that later on has been called stochastic stability. Now, the idea is the following: therefore, if you cannot prove exactly for Sherrington-Kilpatrick, you can prove in a model with an epsilon distance on Sherrington-Kilpatrick. And from this model with a epsilon distance on Sherrington-Kilpatrick, you know that Guirlanda-Guerra distribution are satisfied. Now, it can be proved, I don't remember who proved, that we can restrict in the Heidemann-Simon star formula only stochastic stable P of D. Therefore, we have just a great reduction on the phase space of the original approach, because now we have not to consider an arbitrary distribution over the descriptors, but we can have a distribution, can only look to stochastic stable distribution, which satisfy also the cavity self-consistency equation. Now, it is a relatively simple computation to show that if P of D is stochastically stable and ultrametric, it coincides with the probability distribution of the replica method. So, the point now we see that we arrive to the essence of the problem, and the essence of the problem was to prove that the probability distribution is concentrated on ultrametric trees or ultrametric descriptors. And there was a beautiful paper of Panchenko that proved the correctness of ultrametric distribution. I mean, the proof, Panchenko more or less proves that if you have a probability distribution that satisfies Guirlanda-Guerra, it has to be ultrametric, because if it is not ultrametric, this would lead to some contradiction. Now it's clear that now you have all Talagram proof and so on can be streamlined in a very simple way. You start from SK model, you derive in SK model you derive the Guirlanda-Guerra equation. You prove with Panchenko that this distribution should be ultrametric. Use the Heidemann-Sieve star formula, and you see that this reduced to compute the free energy in terms of the function Qx, because an ultrametric distribution which satisfies the Guirlanda-Guerra equation is the one that we know with Q of x. So everything simplified. And of course, this is great from the physical viewpoint, because it's a clean mathematical proof, which is based on probability and on some identities that have very important physical meaning. I cannot have time to discuss the physical meaning of Guirlanda-Guerra, but they have a clear meaning. And the meaning is connected essentially to Gibbs state. I mean, to the Gibbs rule. I mean, the point in that this system, the Gibbs rule for the number of consistent phase, is related because we have an infinite number of that. And essentially, the Guirlanda-Guerra idea was that you can prove that if the Gibbs rule is related in this way, this may happen only if certain identities are satisfied. Now, we go back to the original point. We have everything is done, everything is understood, but what about the original replica method? I would say that certainly the replica method had has a huge heuristic value, because I would think that if it taken 20 years to prove the correctness of the replica approach, starting from knowing the result, it's clear that without knowing the result with replica theory, it would be very, very difficult to get a Talleyrand proof and also beautiful Guerra, Pachenko, and other proof. So the thing that would be important, if we can use replicas instead of the probabilistic approach to get a rigorous result. Let me describe some approach. I mean, we know from the work of, what is the formula that was quoted before of Sherrington Kirkpatrick? If n is integer, is a natural number, the average value of the partition function to the power n is given by this type of integral. Now, I don't want to use tricks, so let me very precise to what is integer and what is not integer. And of course, I can define here for non-integer, and in reality I can define for complex object, the average value of the partition function to the power z. This object, of course, these two functions clearly coincide when n is a positive integer. Now, the point that the first conjecture that I would like to do, therefore I will not prove anything, but I will only describe some conjecture. The first conjecture is that if you know this function here, that this quantity here is the unique, or maybe one should be more precise, essentially unique analytic extension of this function from integer to complex number satisfies some restriction. Maybe, I'm not sure how this uniqueness can be done. The point is that the Kalman condition, it seems to me that it does not work, because z to the n is proportional to n square, to exponential n square. So the moment problem, the standard way to approach the moment problem is not well, does not work the uniqueness theorem of Kalman. Therefore, this means that one could, the extension to these things here to complex value a priori is not clear, but it may be that imposing some condition can be unique extension, or if there may be a few different extensions, but maybe different ones from the other one. But but not too much different. Now this is a relatively mild conjecture, and now let's come to the real difficult conjecture. Now we define a new function Zn, which is just the sum over all critical point. I mean, if I take Fn, I define a critical point of this function, a point where the derivative is equal to 0. So it's clearly that when you do the set point method, you have to take the standard set point method. You have to take the minimum one, the set point, the minimum, and the sum alpha is dominated by one single point. The idea is that you write this function, you do these things taking all possible point for which this function is stationary. So this is not a great improvement, because when for integer n, is not a great improvement, because for integer n, when n go to infinity, is dominated by the minimum. And now, however, this formula has one advantage. Is if we compare this formula here, where you have the integral of the q, this formula here is an advantage because you don't have the integral of the q, which makes things simple to, I mean, at least one of the things that is very hard to define, the integral of non-integer number of variables, it disappears from this formula. Of course, now the point is this formula, this quantity here that is defined here, is useful, and the first thing that one would like to understand, if there is a unique or essentially unique analytic extension of this function Zn from integer to complex number. I mean, in the same way that this function here was an exact analytic extension, maybe unique or not, of these things here to complex number, maybe there exists also something that may extend it in this way. Of course, this is very difficult to prove mathematically, because maybe you can, maybe you don't need a unique, maybe that you can consider a natural extension. But anyhow, it's clear that this is something quite delicate from mathematical viewpoint, because in order to discuss which is an analytic extension, this function Zn, you have to know essentially to have under some kind of algebraic control all possible type of minima. And however, this is something that is a good question for mathematician. And therefore, if there is a unique or natural extension of this function here to complex, in the complex plane, we can call this function here z of Zn. Now, n, this is here is non. This is not integer. And now the essential point is that now we can have that for any value of n, that you can have for any value of n, that the limit where n go to infinity of this function here coincide with the limit n go to infinity on the other one. Therefore, this means that for any real n, we can control the value of the partition function, the log of the partition function, starting from the value on integer, but not for only one value of a few values, but the set all value. And of course, that will be useful if you have a direct algebraic way to evaluate directly this function without using the probabilistic result. Some step in this direction in one particular case was done by Campellone, myself, and Virasolo. So I think that it will be something that I will dream that somebody could, and also I would like to interest in mathematicians, if using algebraic method, one can put the replica approach in a way that is rigorous, and therefore reprove the correct formula using the original approach. So thank you very much. I have finished my seminar. Thank you so much.
Thank you very much, Giorgio. Let's unmute ourselves and applaud Giorgio. So maybe, Giorgio, maybe you can stop sharing so people can ask questions.
Yes. The point that I have to find where I have to stop sharing, because I'm lost I've lost the window. Or you can take out my ability to sharing, maybe.
I don't know. August, can you do something? But anyway,
okay, we're done. Okay.
Very good. Thanks. So, are there any?
Thank you.
Are there any questions somebody wants to ask? Tom, you want to ask a question?
Oh, well, I was just wondering, what about dynamical approaches to SK and other models? Do you have some comments about that?
No, this is a dynamic approach is certainly very interesting for the physical viewpoint. And I think that is absolutely correct. It was very clear. It's a very, very nice formulation that was done mainly by Culiandolo, Kurchan, and also before in a slightly different formulation by Somponiski, and so on. The point that my idea was to speak of something that can be proved, and I'm not have any idea on how the dynamic approach may be transformed in a rigorous proof. But maybe that I don't know.
Okay, thank you.
Are there other questions? So, Giorgio, what do you see then as the most likely breakthrough? Is it just what you were saying?
Well, I don't know. I mean, the things that really would be a good breakthrough would be the control of finite end correction. Finite end correction are very difficult to control. And also and indeed this corresponds to control in a systematic way the correction in finite dimensions. In finite dimension, we know that we have a very complex computation that was done by Condor, Temchevari, the Dominicis Condor, the Dominici Condor Temchevari, on the correction to the loop, two corrections. They computed the equivalent of the propagator of the two-point correlation functions. However, the thing that would be really a breakthrough if we could write some manageable formula for the loop from the loop correction. The first attempt of the Dominicis was tamed by the fact that they had in their approach or the 10 to the 5, 10 to 1, or 10 to the 6 different terms. And that was much higher than their capability to do computation. And I think that what will be very important, it will be really breakthrough if we could do corrections, finite volume correction, or better finite dimensional correction using some formula that can be controlled by men in a reasonable way. For this point of view. Of course, after the breakthrough are all possible applications that you have seen to statistical mechanics and to many, many other subjects.
When you say finite dimensional, you mean short range interactions?
At least, I mean, a finite dimension short range interaction, at least the perturbative expansion around mean field. The perturbative expansion around mean field that we know how to do very precisely in the ferromagnetic system, and it's something that cannot be done in this way. This is very important because we know that the perturbative correction around the mean field were essentially the starting point of the diagrams that Wilson have used for the renormalization group. So in the end, the breakthrough will be to a precise formulation of the renormalization group in finite dimension, because there is also critical point, which is the lower lying, the minimal critical dimension, lowest critical dimension. And we know that, for example, for ferromagnetism, Ising case is 1. In this case, there are some indication from simulation and so on that the lowest critical dimension is between 2 and 3. Some suggestions that is 2.5, but it's very difficult to give any, I mean, one can do some analytic computation in this direction, but it is difficult to have a more sound idea. And also the other things that also need a lot of work to prove or disprove, I think that I would prefer prove, that replica symmetry breaking is correct, for example, in 26 dimensions.
I see.
I mean, it's very well approximated. What we know that from simulations that the systems with 10 to the 1,000, sorry, with 1,000 millions of spin, also from experiment, behaves like what happens from replica theory. The point is that one is to understand that the system, it works well in according to mean field theory. For example, if we take the ferromagnets, Heisenberg ferromagnet, low temperature, the description of Heisenberg ferromagnet, low temperature is extremely good, starting from mean field theory. The only thing that you discover from mean field theory that at the end, when the volume becomes really infinite, the system becomes again symmetric, and symmetry breaking does not happen. But also this does not mean that in real experiment you don't see replica symmetry breaking, but you have to understand that real experiment can thermalize only system with 1 million atoms. Therefore, you can see that the real experiment describes this system of that size, and what happens not when, and 1 million is not infinite. So the problem, there's a problem to understand what happens when it really happens with infinite from mathematical viewpoint.
I thank you. I see there is in the chat, Robert McKay wanted to ask something. Are you there, Robert?
Hello. Yeah, it's just that there was an example I heard back in 1991 where someone used a replica trick, or maybe it was cavity method, I forget which. But anyway, I could see the result not true. And so the question is, what restrictions do you think might be required in order to apply the replica method?
Well, I don't know. I mean, I think that I think that it works in most of the case. In some cases, it may not work, but one has to look carefully why it does not work. You know, I started to be very interested. I mean, all the work that I done on spin glasses was not done because I was interested to spin glass. Reality, when I started, I have no idea what spin glasses were. I read only something on Newbensky, on a paper on Newbensky on branched polymer. I was interested in branched polymer for a reason connected to QCD, a work that was doing with Nicolas Soulas, with Druff. And the reason that was interesting to this type of problem, I discovered for QCD, I discovered that Newbensky says that this type of computation could be done with replica, but the replica method sometimes gives the wrong result in the case, as in the case of the Sheraton particle. So I say, what a shame that the mathematical method gives the wrong result and we don't know why. So I start to say, well, I think that this is something that must be fixed. And well, at the end I fixed. So if the replica method does not work in some case, which may be quite possible, I think that one should understand why it does not work, and deeply, and which are the other kind of system for which it does not work, because not all method works not in every situation.
Okay, thank you very much.
I think there's a question by Nigel. Nigel, wanna?
Yes, I have a question. So I wanted to ask you about Berger's turbulence. So as you showed maybe 20 years ago or so, in Berger's turbulence, there is a one-step replica symmetry breaking. and at least in goes to infinity dimensions. And I wanted to ask you what you thought was the physical interpretation of that, and what you thought, whether you thought Navier-Stokes turbulence would also have a replica symmetry breaking of some sort.
Well, I don't know. I really don't know, because the way that we do look into Berger turbulence, essentially the replica things come from the possibility of writing things in terms of direct polymer, and you can discuss therefore this is some kind of statistical mechanics problem. If I have to discuss it in terms of turbulence, I do not find any way in which I can connect real turbulence to some equilibrium quantity of a well-defined statistical method. Maybe there is a way to do, but it is beyond my ability to see it now.
Okay. Are there any other questions or comments?
Can I ask a basic question?
Yes, please.
Yeah, my only question is actually a very basic question, that are there sure signatures of the situations where physics disagrees with mathematics or the other way around, but still physics leads to the right answer? I mean, physically correct answer. Is it okay? So one possible answer probably is, I haven't thought much about it, is it near the singularity?
Well, I mean, the point, if I understand you correctly, I mean, from the physical viewpoint, the thing that the most clean experimental signature of replica symmetry breaking were that the equilibrium susceptibility goes to a constant when the temperature goes to 0, while the magnetic susceptibility inside one state goes to 0 when the temperature goes to 0. And this was something that was known from the very nice analysis of the TAP equations for SK, that the susceptibility inside the state was going to 0. And the fact that equilibrium 1 is not going to 0 is something that can be seen very nice experimentally, and is one of the way that you can see that there is something deep in the theory, because you have the situation where the linear response theory does not work as it should do.
Okay, thank you. Thanks very much.
Are there any other questions or comments? If
Can
not,
I ask a question?
yes, please.
Apart from strongly disordered systems, where is the replica method also, can it be applied to systems that are regular, that don't have disorder? Are there such examples where this application can be really traced?
Well, one of the most nice applications of the replica method has been done for glasses for hard sphere. Now, you know that hard sphere do, well, this is some way cheating that there is no disorder, but let's say, suppose that we take a glass or a system of hard sphere, and suppose that we cool it very, very fast. Now, if hard sphere, if they are cooled very, very fast, do not crystallize. I mean, we know that hard sphere, I mean, I think of identically hard sphere, do crystallize if they are cooled slow, if they are cooled extremely fast. But I mean, to such a speed that cannot be done with real experiment, they do not crystallize, and they go inside they are completely frozen. And now, if we look to this, to the oscillation, to the behavior, and of this system, we send the pressure to infinity. We can apply the the replica method, and we obtain some results that are very good in agreement also with some colloidal system. Of course, real colloidal system have not exactly the same radius and so on, but also one can argue that this type of result can be applied to systems, to polydispersed system. And therefore, I would say, yes, if there's all apparatus of these ideas that can be used for glasses and for near jamming, if you are looking for continuous symmetry breaking, where the function x, q of x is a continuous one, if you just look for this continuous from one step replica symmetry breaking, there has been all the work by Patrick Tivomelai and Walliness. We showed that all the more coupling transition can be reinterpreted in terms of one-step replica symmetry breaking. There are all these predictions that can be done in that direction. So it really works in a lot of cases. And the reason is that in this case, the system generates its own disorder, and it is frozen inside one of the many, many disordered phases in which it can stay.
Okay, are there any other questions or comments? If not, let's give an applause to Giorgio, thank him for a nice seminar and congratulate him on his prize. And see you next week. Bye-bye.
Goodbye.
Bye-bye.
Bye-bye. Thank you.
Bye-bye. Bye-bye.
Bye, goodbye.
Bye, everybody.
Bye, everybody.